Hello, and once again, welcome to the 13th class, 13th 1-3 class on coordination chemistry. And in the Zoom, we are joined by Udit, Satya, RS, means Riddhi Siddhi, Prabhat, Krishna, Girija, Amlan, and many others to join. And soon, we will be joined by some watchers, viewers from the YouTube source, and later many. Last time we had a very fast discussion on the CTS. Of course, I'm sure about the DD transition, how to get the complementary color. Once you are given the lambda max value, you can know from which region it comes. It is absorbing, and looking to the color wheel, you can predict the complementary color. That part is okay. But the most intriguing part in the color exhibited by, particularly those which have pi acceptor, pi donor characteristics, like cyanide complex, carbonyl complex, these have a dominant CTS. Charge transfer spectra, we have not written anything. We have understood but not written anything. Let me share my screen. And I told you that we will write a few words on CTS. Have we written anything on CTS?
No, sir.
Okay. Coordination compounds. This was our last class. No, this was our last class. Yes. Um, and those which are D0, D10 configurations are usually colorless. But you will not be 100% sure that they are really colorless. Usually, they may be colored due to CTS, particularly the oxoanions, permanganate, manganate, dichromate, chromate. They are all vanadate. They are all D0 configuration. Vanadil, D0 configuration. They don't look like complexes. They are normal oxoanions, but they also split. Oxide ion, we don't say a tetraoxidochromate 4, chromate 6. We say chromate. That is the normal name, common name for chromate ion, but we can call it tetraoxidochromate 6. And it's a tetrahedral complex, CrO4 2 minus. So they are colored due to CTS. And if somebody says why ZnCN whole for 2 minus is colorless, why CuCN whole for 3 minus is colorless, there are three D10 configuration. D10 configuration has no role for DD transition. They are incidentally, they are also colorless. But they have a strong CTS which fall in the UV region. They don't come to, since D is full, it has to be a metal to ligand MLCT. One electron from the metal D, higher orbital EG, that will be transferred from the metal to the ligand antibonding vacant orbital. So if it is completely full, then you have a CT, that is MLCT, but that will be falling in the UV region, nothing will, but some of the complexes, particularly the copper 2 plus complex like this, is colorless. But some complexes of cyanide complexes. They are colored even if D9, D8, D7, D10, they are colored. If it is light yellow color, then you are sure it is due to the tail portion of this strong CTS peak. This is either both MLCT and CTML. Only MLCT is possible for D10, but if it is D9, D8, then MLCT, CTML are possible for pi acceptor ligands like CO, CN minus, NO2 minus, SCN minus. So it is very complicated, but you must know what is CTS. So let us write down in a new page without looking to welcome those who have started watching from the YouTube. One viewer has joined. Um, uh, Start a new page. Oh, this is view. Make it 100%. Okay. CTS, charge transfer spectra. I think we have written types. Commonly, this is LMCT, ligand to metal charge transfer. I think we have written one sentence, I think, about MLCT. No sentence. B, MLCT, metal to ligand, and very uncommonly MMCT or intervalence charge transfer, and most uncommonly LLCT, ligand to ligand. This is metal to metal. It is also called intervalence. And this is ligand to ligand. One electron from either ligand or metal, or I'm not writing to make it complicated, is transferred to metal or ligand respectively, and absorbs certain color. It has got a lambda max, and we observe that theory of, you know, color holds good for DD transition for CTS. Once you know what is lambda max, you can know what will be its complementary color, particularly oxo anions. They have their lambda max, CTS, strong lambda max in the visible region. But cyanide, carbonyl, they have got a equally very high energy CTS, lambda max. The entire mountain, entire spectrum, wide spectrum falls in the UV region. We observe its complementary color. And this is usually a P to D transition, which is highly allowed. You know, it gives the most intense peak. peak intensity, hence the color may be complementary, goes in this order. One is CTS, whatever may be the CTS. It is a P to D or D to P transition. So del L change in azimuthal quantum numbers would be plus minus 1. I'll write down that the selection rule, how the selection rule breaks down partially so that in octahedral field DD transition is partially allowed. So we can we can twist the rule as we are very close to a politician, a minister, then we can bend the rule according to our convenience. Partially, but not you can't completely violate the uh, constitution. I mean the um, rule. I mean the laws. Those are written in the constitution. We may bend the interpretation in a manner that will benefit us. So CTS spectra is most intense, followed by TD, tetrahedral complex, followed by OH and SP. They belong to one category. Sometimes OH, sometimes SP, sometimes between OH, sometimes someone, the epsilon max, this is absorbance, is greater than 1000 to 10 to the power 6. Epsilon max is called the absorbance. That is a constant for that particular absorption. So I will tell you the beers, Lambert's law, not the beer that we take for a narcotic, for having fun. CTS, the epsilon max absorbance intensity of absorption, if very high, highest, so the color also, the complementary color is also deep. Followed by this is maybe max 10 to 100. What do you remember? I had shown you the slide. What figure you remember? Anyone? What figure you remember? Tetrahedral complex, epsilon max. Can it go to 1000? We'll check. But this will be about 1 to 20. So low intensity, very weak, peak, as well as the color is very mild color, very faint color, weak intensity color. This is moderate, and this is this. And let me introduce first the LMCT before I tell you something very. The oxo ions are mostly D6, yes, D0, but colored due to CTS. LMCT, ligand to metal. For example, permanganate is purple. Supposing you are asked a question, the purple color of permanganate is due to A, DD transition, B. Of course, if details will be given MLCT, LMCT, so it will be LMCT. This is purple. Chromate is yellow. Dichromate is orange. And can give you some more. Yes, yeah. And you can write down this vanadate ion, VO4 3 minus, yellow, and this is a cation, VO2 plus, vanadil, that is yellow, and this is not 5 plus, it is not D0, it is D1, because it is not, uh, vanadium is not in plus 5 state, it is in plus 4 state. So this one has one electron, but all others are D0. These have, excepting this. You cannot write something wrong. These except VO2 plus. VO2 plus vanadium is 4 plus, plus 4 oxidation state. So it is still D1 configuration. But VO2 single plus, that is D0. Chromium is plus 6, D0. In both chromate and dichromate, it is plus 6. And vanadium, in vanadate ion, it is plus 5, D0. This is plus 6, plus 6. And this is plus 7, D0. There, because L, MLCT is not possible. For MLCT, it should have a antibonding orbital. Oxide ion, chloride ion, bromide ion, they have non-bonding electron. They can go for pi donation, but not acceptor. So MLCT is absolutely not possible for these oxo ions or even chlorido, bromido, iodido, if they are colored due to CT, charge transfer. It has to be LMCT, ligand to metal. Similarly, these are not complexes but compounds of transition metals. CTS is yellow, mercuric sulfide, ferrous oxide, all these transition metal compounds, sulfides, oxides, they are colored because of CTS. And here titanium tetrabromide is orange, is deep orange, intensely orange color. It is not due to DD transition. You can't say tetrabromido, titanium 4. You can call it. There is no harm in telling tetrabromido, titanium 4. You can call it. But the color is not due to DD transition. Because this intense color, sometimes you have to know the epsilon max value. This epsilon max value has been found out to be much greater than 1000. Therefore, it was confirmed that yes, no, it is not due to DD transition. This is, and in fact, D0. It is not possible. In this case, the only argument that you can do is only this. The only argument you can do, not that, I'm sorry. This one, which is D1 configuration. Vanadium is in the plus 4 state. There you can make an argument. How can you prove that it is not due to DD? There is one D electron, it could have gone. From the intensity of the peak, from the absorption peak itself, it will prove that it is not due to DD. DD peaks are very, very, this is like some little hills that you find in your locality, some little hills. But Kilimanjaro, Himalayas, so that is CTS. So these are all titanium plus 4 is D0. They are all colored because of this. Titanium chloride, tetrachloride is not colored, fluoride is not colored because the CTS doesn't fall in the UV region, in the visible region. If the CTS also falls entirely in the UV region, then no color can be found. So that you can write down. Just write down other transition metal compounds are colored due to CTS. Example, you can give an example. So I have given this, I have already told this, LMCT is very strong, I have already written this. Factors you need not write. What factors depend on? LMCT is prevalent. Most of the compounds of transition metals are colored due to LMCT. Only the complexes cyanide, carbonyl, thiocyanate having pi bond, pi acceptor capacity is there, they can show LMCT and MLCT both. So these are not very important, depends on whether on the size of the ligand, that I have already told you. I am not going to repeat this. These are all +7, but the energy, and you expect if maximum energy is per Rennet ion, all are D0. But if at all you expect some color, then permanganate. You may not expect any color in because the energy is more, the entire absorption will fall in the UV region. So I have also given the reason behind everything. You can read. So if perrhenate ion is not giving any color, but permanganate is giving a deep purple color, it is because uh, it is not because there is absence of any transition. There is there is CTS, there is LMCT, but that falls in the UV region. That is why perrhenate. Similarly, tungstate ion, supposing, is colorless. Is it colorless? Molybdate also color, but chromate is yellow, because all these have higher transition energies. CT transition energy is more, and the corresponding lambda max falls in the UV region. Entire mountain falls in the UV region, and so these are the factors which I have written. Why chloride doesn't give? Because chloride, the titanium tetrachloride doesn't give, because the energy is high, lambda max, the mountain falls in the UV region, while bromide, titanium tetrabromide and titanium tetraiodide gives color. So these are the factors. In the transition series, there is a slight change. As you go from left to right, it will decrease, and the possibility of the peak entering into the visible region will be more. But no, all these are colored, we know, but the transition energy will be less and less as you move, the size decreases. So MLCT, let us write down. For MLCT, this requirement is LMCT, high oxidation state, so that the metal ion is ready. It has either some no d electron or at least 1 2 d electron, so that it is ready to accept. So we will write down that high oxidation state with a no d electron or at least 1 2 d electron, and the ligands should have a lone pair with a negative charge with pi donor capacity. Acceptor capacity, if it happens and there is a d electron, more d electrons, then the MLCT will be, probability will be high. So it's a lone pair which can be donated. It's called pi donation capacity. So then we can write down the MLCT shown by high OS, and that means no or small number of d electrons in metal ion, and uh, negative ions like O2 minus, OH minus, Cl minus, Br minus, having non-bonding electron pair for pi donation. The pi donation word I am saying in terms of the ligand field theory, or MOT. Into the second is MLCT, metal to ligand. That case, it is for metals with low oxidation state including 0, +1, maximum it can go to +2, not very high, and with pi acceptor ligands like carbon monoxide, Cn minus, SCN minus, NO2 minus, this, which have got pi star vacant, pi star antibonding MO. I'm writing orbital, actually it's molecular orbital, to accept electron from larger number of d electrons. Most carbonyl complex cyanide complex are colorless. And other complexes having this pi acceptor ligands like nitrito are colorless. Despite having non D0 configuration, sorry, non D10 configuration. Because CTS falls in the CTS and DD. Because if it is non D10, there is a possibility of DD. A small peak that is buried. Both have high energy, so they are buried. The DD is buried inside. CTS and DD peaks entirely fall in the UV region. Even some cyanide and carbonyl complexes, some such complexes are light yellow in color. Why? Some carbonyl complexes, such complexes are light yellow in color, very light yellow in color. Example, the example is hexacarbonyl chromium 0 is light yellow because the strong MLCT peak has a tail entering into the violet region. If the tail enters into violet region, so the strong peak, supposing this starts, this is UV, this is visible, so this entire peak is violet region. This is lambda increasing, this is the absorbance known from the epsilon max value. The absorptivity, what I have written, epsilon max, absorbance and absorptivity, that constant. Sometimes people call it molar extinction coefficient in the olden time, absorptivity. Just like conductivity, resistivity, this is absorptivity at a constant. So, such complexes show both MLCT and LMCT. If it is not D10, if it is D10, it can't accept MLCT. So it's very difficult to say which one, because both LMCT and LMCT are possible for such pi acceptor ligands. So that is all. And let me tell you that the Beer's and Lambert's law tells about the absorbance, how intense an absorption peak will be is directly proportional to concentration and the length of the tube in which the solution is there and the light is passing. Uh, you know, white light is passing, white light is passing, it is absorbing some color, and the rest is transmitted, and we are looking to the transmitted color, which is the complementary color of the color which is absorbed. So, uh, uh, and the proportionality constant is epsilon. This is called, this is absorbance, which is variable depending on concentration. This is concentration of the solution whose absorbance, the compound taken in a solvent which does not absorb in the UV visible region, concentration of the solution, L, the length of the uh, cylindrical tube uh, containing the solution, and epsilon is the absorptivity. So selection rule says, I'm just telling you what I told last time, that an electronic transition, this is Laporte selection rule for electron transition is allowed when delta L is equal to plus minus 1. P to D or D to P is allowed. S to P is allowed. But if these transitions are allowed, or P to S, but P to P, D to D, S to S, these are banned, forbidden. Forbidden, don't take it literally. We have some rules to break down. These are forbidden means they are not allowed to that extent. And this rule is strictly valid for having those having G symmetry, G-rayed symmetry. What is G-rayed symmetry? What is G-rayed symmetry? What? Are G symmetry, G-rayed symmetry, what is that? Are you listening to me?
Yes,
Are you
sir.
guys are here or I am talking to no one? G symmetry is what?
Jared symmetry.
What is that? What is that? Amlan? G symmetry is what? I have told you 100 times.
सर
What?
जो लिगेंड प्रेजेंस रे डी ऑर्बिटल टा डी टा बारी सेंटर और
You guys have become very, very less responsive. What is G symmetry? I have written it is inversion center. If any molecule has an inversion center, it is called G-rayed symmetry or G symmetry. An octahedral having octahedral geometry having all the ligands same, metal at the center has a point of symmetry, and that is called G symmetry. Have I not told you G-rayed, un-G-rayed, G-rayed, GEG, G-rayed symmetry? G symmetry stands for any molecule having a inversion center. You know already there are 4 elements of symmetry. I have introduced to you all the 3 in details, but only SN I have not introduced in greater detail, but I have told the presence of Sn, I, sigma will make a molecule achiral, but the presence of Cn will make a molecule chiral, or absence of these 3, sigma, Sn, and I will make a molecule chiral, which is optically active. Have I not told you? So what is G symmetry?
Inversion center.
Molecule having inversion center.
Yes. So tetrahedral geometry that doesn't have, since even if there are four identical ligands, it doesn't have a G symmetry. Since that is the reason why we don't write the subscript EG and T2Z in the tetrahedral splitting. Only write T2 upper and E lower, just the opposite. You are not revising anything. You are just attending like a history class. History class. Since TD geometry lacks G symmetry, Laporte rule, selection rule is partially allowed. Partially, very partially allowed. So that is the reason why the intensity of tetrahedral complex is little more. It is not totally allowed, it's partially allowed, because this rule is strictly valid for those having Z symmetry. Those geometry that can have a point of inversion or a center of inversion or inversion set. And another spin selection rule is there. So allowed transition should be not only having del S is equal to plus minus 1, but the spin change should be 0. Whatever was in the T2G set, it will be just lifted up with the same spin without inverting the spin. That is disallowed. That happens. That also is partially broken due to something, due to spin orbit coupling. Allowed delta S 0, del S non-zero is forbidden. But partial breakdown of the selection rule occurs. Those reasons will not write down here. It's not required at all. For some reasons for which DD transition is partially allowed. Hence gives lower intensity peaks, intensity color or light color. Everything, blue, green, whatever color that you predict, only due to DD transition is DD transition is weak. But between them, you have to compare if in some complex it is spin allowed or spin forbidden. If spin allowed, then intensity is little more. Tetrahedral, in tetrahedral, a transition usually takes place from the lower set, that is EG to T2G. So where in most of the metal ions, the spin from the T2G set, which is the EG set, will remain the same. Will supposing C, cobalt, cobalt, this is a TD complex because this is a 3D metal ion and this is a weak field ligand. So this is D7 configuration. And once you know it is a TD complex, then your splitting will be, the EG will be below and T2G will be up. T2G, I'm so sorry. Just up before few seconds, I was telling you that there will be only E and T2. So if there are 7, then del T is very less compared to pairing energy. So hund, then poly, poly. So these two which are unpaired, I mean paired. So one of them will go and without changing in spin, it will be here. So del S will be equal to 0. So this is a allowed transition. Sone pe suhaga. First of all, it lacks G symmetry, for which the Laporte selection rule for the delta L is partially allowed, partially, and it is spin allowed. I told you even for two octahedral complexes, one having little more epsilon max, one is less epsilon max, that can be found out once you split them and see. Supposing you have a configuration T2Z and EZ, uh, so it has to flip. How? Tell me which configuration it has to flip. Supposing here, there is nothing here. Now, the electron which is paired has to leave because there will be a lot of repulsion. If it will leave, then it has to go for the same spin. It cannot remain because the Hund's rule will be applicable individually in each set. So, this will go, this cannot go. So this will go, it has to reverse its spin. So this is spin disallowed. So this is a this 5 configuration, manganese 2 plus. The color will be very light because spin uh, transition is forbidden. It will happen. Breakdown of even spin selection rule happens due to LS coupling, that you forget about it. But supposing you have this is a high spin complex. High spin complex, you uh, D6 configuration high spin complex, and there is vacancy here. So this one which has to unpair, one of them will go in the same one of them will go in the same spin. Uh, no, supposing we have a nickel, there are 2 electrons here also. Then this one will go and it will pair this. So this was anticlockwise, this will also remain anticlockwise. So in this case, in D8 configuration, there will be no change of, but in other case, there is a change in delta S is non-zero, then it is a violation, it is a disallowedness of the spin. So with this in mind, you can predict. Of course, this will not come in your even NEET examination also. This will not come. This subtle difference between the intensity of color in two octahedral complexes, which are both octahedral, but you have to first judge whether it is high spin or low spin. Then you draw the splitting pattern and see whether there is a spin forbiddenness for both. Laporte selection rule is forbidden, but there is a breakdown of the Laporte selection rule, partial breakdown, for which DT transition is occurring. But between the two, if someone has a little more intense color, then it may be due to allowedness of the spin. Del S might be 0. In some case, some example I have given, you can see. So with this, we conclude this part. You see, I have given one example here. Yes, then intervalence, that also we must write down a little bit. A third category, MMCT. or intervalence charge transfer. This is say Prussian blue K, Fe, FeCN6. Some people write Fe4, same thing. Yes. The inner is +2 and outer is +3. This is ferric ferrocyanide or potassium ferric ferrocyanide. This is Prussian blue. That is neither DD nor LMCT nor MLCT. LMCT is this ligand to metal ion inside the coordination sphere. ML, this is LM, and ML MLCT is from metal to ligand. Both are occurring in cyanide complex, both are occurring, but both fall in the, it has been already found out experimentally, they fall in the UV region. But the color that we see, ferrocyanide ion is, orange red in color. That is not due to that. It is due to electron coming from ferrous to ferric, electron transfer from ferrous to ferric. So this is called intervalence or metal to metal transition. One inside the coordination sphere, the other outside the coordination sphere. Same is the case with the Turnbull's blue. It is opposite. Ferrous ferricyanide, Fe3, FeCN2. Or you can write KFe. This is +2, this is +3. Ferricyanide, 6. So this is 3. So to maintain, you may not give anything. KFe, FeCN whole 6. Formula is same, but this is called Turnbull's blue. This is +3 and the total is -3. But you have prepared by other method by adding ferrous sulfate solution to potassium ferricyanide. But here we have added ferric chloride to ferrocyanide. But the composition is same. One is called Prussian blue, the other one is Turnbull's blue. And here, electron goes from ferrous to ferric, turns blue. Or some people write ferri means Fe3, FeCN6 whole 2, ferrous ferricyanide. Similarly, red lead and magnetic oxide, all these are colored due to intervalence charge transfer. And the ligand to ligand charge transfer is extremely rare. You should not bother about it. And one example I was really desperately wanting to show you about, that absorbance is formula actually, you can write down I0 by I. I0 is the intensity of incident light on that particular solution, and I is the intensity of the transmitted light, and that ratio and the log of that is called absorbance. That is equal to epsilon into C into L. So just write down is equal to log I naught by I. I naught is the intensity of incident light and I is the intensity of transmitted light. What? Yeah, we have all done everything. Yes, 1002, 1002, 10 to the power 6. Let me see whether my memory and your memory is going well, or so we are having some dementia. Yeah. I'm yet to become, but yes, little bit of dementia. Uh, this is 50 to 150. And the octahedral and square planar, most ghatia among all, will be uh, 0 to 10. 0 to 10. I have given a little bonus 20. Let it be. I was talking about manganese complex compared to cobalt is D7, it is 1 to 10, and this is 0 to 0.1 epsilon. So this is, I was, D5 configuration, high spin, hund, 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 hund. So this has to go to the upper with inversion, because two electron cannot remain with the same spin. It will violate Pauli's exclusion principle. So it has to invert. So because it has to violate the spin selection rule, its intensity is least. But here D7, and that is also high spin. Cobalt 2 plus is not strong, and water is a intermediate field ligand. So this will be hund, 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 then poly, poly. So one electron will go, it will go as such and pair the other one. This unpaired electron from any of the two pairs will go without change of spin and pair the other one, the higher one. So del S is equal to 0, no change in spin quantum number. So hence this is allowed transition. That is why the epsilon is little more. So today, I think I have given a lot of things to do. Have you done that? I think I have shared this file to you. Have I, Krishna?
Yes, sir.
So you have taken these classes very lightly. If you have done so, then this will be the last class on transition metal coordination compounds. If you are taking so lightly, yes, you are leaving the class. Some of you are leaving the class because you have some other coachings and all that, and because it is recorded, you view it, watch it, see with all seriousness later. But if you don't do the home task I give you, then what is the need of having these lectures?
Sorry, sir.
Then
Sorry, sir.
today's program was completely different. That is stability of complexes. There, today, how can you come so confidently? These are new other students which you have met, but you have not seen them. No, I will not take this pita. Amma has given.
No, I just got it.
Will you chat with me? I will stop the class. Okay, that is your intention to sabotage. Huh? Hey, show your faces. No, this is a recorded class. This is being live streamed, and in this live streaming program, you are coming to disturb me and to trouble me and to meet my students. Huh? Yeah,
Because I'm a big girl.
you are a big girl, so you will come to the class. So you want them to show their faces? Hmm? Oh, Krishna, Amlan, please open your videos. Say hi. This time you will say hi. Say hello, Krishna. And many have gone already. Class is over. Okay, bye. So you go, and I'm going, just joining and playing with you. So today we will not do in a hotchpotch the stability, which is thermodynamic stability and kinetic stability, with a lot of factors which influence the stability of complex: stability constant, the instability constant, that is dissociation constant, and the 5-6 factors, main factors. Although I have listed 9 factors, but the main factors will be 6, 7, 6. So that we will discuss that maybe tomorrow. I think. Is it possible today we will discuss or tomorrow? Krishna?
Sir, tomorrow.
Okay. Bye-bye. But if you don't,
Thank you,
you
sir.
know, if you don't revise whatever I have taught so far and whatever I have given you as a home task, little bit, I will give you many more home tasks, MCQs. Then this is the last class. I will be playing with my granddaughter. Bye-bye. Thank you very
Thank
much
you, sir.
for those who are watching and
Thank you,
who
sir.
are watching at a later stage. If you have benefited, then please don't hesitate to subscribe to my channel. Bye-bye.
Thank you, sir.